Okay, well, hi everybody. For those of you who don't know me, I'm the last name on the list there, Scott Northrup. I'm one of the other analysts here at SciNet. And I'm going to be doing a few of the next sort of sessions throughout the next few weeks, mainly around some of the parallel performance and some of the parallel type topics, the MPI and some of that type of stuff. So today we're going to get into specifically performance, but we're talking about profiling, but basically how to measure what you're doing. The previous lot of the course has been about how to go about doing it, but the whole part of HPC is usually it's something that's expensive, and you want to know, well, how well am I doing? Is this? Can I make this? It works. That's the first step. But then, how do I measure, and how do I know if I'm doing it in an efficient way, or could I do it better, or anything about that? So we're going to talk about the idea of profiling codes, and also some of the tools you can use to do that. This is not exhaustive, but it's just more of the main sort of ideas around it, and we'll point a few tools that you can use for doing that. Because this becomes very important, and this is not even in the context of parallel performance, just performance in general, because a lot of performance in parallel comes from just having a good serial code. Okay, so there we go. So I'm just going to talk about profiling in general. Then we'll talk about specific things, just the basic time command, very most popular one, gprof, which just builds out of when you compile the code. We'll talk about Valgrind, which is an open source memory tool, and not just a profiler, but it's a memory tool in general for finding things about memory. And then we'll talk a little bit at the end about some commercial products, either the Intel vTune type tools and Allinea, which is a debugger, but also actually can give you some performance information as well too. So just kind of step through from very, very simple through much more complicated in detail, and just talk about in general the idea of how do we measure things, and how do we either find slowdowns to it, or find improvements, or just find where we're spending time. Where should I focus my time on, right? Because if I look at my whole code, I've got a couple thousand lines of code, how do I know what function's important to spend my time, looking for performance? Because if it's just some IO routine that run once, who cares, right? But if it's something that's spending 99% of the time and you're hitting it in some iteration scheme a billion times, well, that's probably somewhere you want to spend time. So instead of just, you kind of know in most algorithms where you'd expect it to be, but you may not know it. So this is a way of being a little bit of a, computational experimentalist a little bit, where you actually can profile and test it out, make changes and run it and compare it in not just it seems faster, but in an actual quantitative manner. So profiling is said it's like debuggers, but it's an evidence-based method to find performance problems. So the whole idea, you can't really improve if you can't measure it. So commonly, and this goes into parallel programming too. We'll talk about scaling, not today, but in general. I mean, we want to know how well it's doing to be able to tell how we can improve it. So the fundamental job of profiling, and unfortunately you can't read that very well at all. It doesn't matter. It's just some code that's just from an old slide there. But the idea being is where's time in your programs being spent? And this is just an approach to do that. You want to find expensive parts, and don't bother wasting your time on most of it. And in scientific applications, that's usually have a good idea, especially if you're developing the code yourself. But you may not, or you may not sure where. It may be an IO bottleneck that you're not really sure of. Or you scaled up the problem and now you're running a much larger problem than you did before, and it can move the bottleneck. Commonly, and this is commonly an issue we have when we teach these courses, we use these toy 1D problems, right? Well, they perform very, very differently than in some 3D realistic problem. Because, you may spend all your time in an IO reading or whatever for some toy problem, but in the real problem, suddenly things go up by the cube of your dimension, and suddenly that's all your overhead. So what you could get away with in serial or in your small problem didn't scale up. So having the idea of doing this profiling and taking it on the small problem, medium size, and scaling it up, you can kind of see how your algorithm will scale up with that program. And also you've built in a mechanism so that as you grow your problem, you can now find different mechanisms out there, right? So this will help you find bottlenecks and find where to spend your time. Now there's two sort of general classifications of profiling mechanisms. You can trace it or sample it. And it's basically, whether I can follow it every exact iteration, or I can just do some sort of general heuristics. And there's pluses and minuses of both, and we'll talk about those. And there's also some that are instrumented, where you go in, or a tool goes in and actually puts stuff in your code, so that it actually instruments the code. So that's like you putting in print statements and seeing where it is, or just doing it externally. And there's pluses and minuses to both of those. But you'll see different tools, and you'll see this terminology, and we'll use that throughout today. So that's just what I wanted to point out. So a very simple, non-instrumented, non-changing way is just run the simple time command. In any Unix type system, you can just type the word time before anything you run. This will just tell you what went on. So you just, like, you can put date and then run your code and then date, but if you run time, it'll actually look at when it starts that thread and when it finishes it, and it'll actually tell you something about it. And the very basic thing it'll tell you is just the total time it used, but it also gives you some details about that as well. So we're just talking about serial codes right now, but so single thread serial code, and it'll tell you sort of 3 pieces of time, not just the total time, but this is wall time. So it'll tell you the real time, the actual total elapsed time. It'll tell you how much time you spent doing something, and how much time you spent waiting doing something. So most of the time, you want these two to be as close as possible, because then you're not waiting for the system to do anything. And invariably, anytime you're waiting a lot on the system, it's almost always you waiting on some sort of I/O subsystem. So you're either calling too much I/O, or you're reading a lot of data. Sometimes you don't have a choice, but that's really what's going to come up. When you're going to see, that's usually what you're going to find out. So if you're running your real code, and this is basically no cost to you. So even if you're submitting jobs to SciNet, you can always put time command in there. It's not going to hurt you at all. It's just going to give you a little extra time, a little bit extra information, and you don't have to back it out. And then if you have that information, you want to do scaling analysis in the future, you've at least got some sort of thing. There's zero cost to it. And you can run this periodically too, to say, okay, well, now something's changing, even just maybe 30%, or so 20%. You may not know that, but if you get in the habit of doing this is an instrument-free thing that's easy to do. And it's available with effectively zero cost. Right? I said if you're doing this in parallel, you could just do this times your real times the number of processes to find your total time that your job's taking. And so then you divide that by your serial time, and you can sort of get a rough basic scaling analysis for zero cost. So it's another little simple command that most people may not know about. Some of you do, but it can tell you, or it can diagnose even very quickly something like an I/O problem. You're like, well, this is taking a long time. It takes 10 minutes to start my code. Well, is that really just maybe I'm doing a lot of initialization, or maybe I'm just waiting on a really slow I/O subsystem, or the way I'm reading it by files? And you can pretty much, you're not going to tell you exactly, but you can take a pretty good guess from something like that. So that's sort of your 0th order profiling scheme, just figuring out how long something takes. You can also do this actively a little bit by using a nice little tool called Top. I imagine that some of you guys already have used this before, but Top is just an aggregator of what's going on in a system. If you ever log into a node and we all the time, you're like, wow, this seems slow. You type in Top and you can see what's going on. And it's a list of all the running processes, and there's a whole bunch of options for Top. It's just a little text user interface here. And it'll tell you a bunch of details about these are all the processes are running. This is like you typing PSAUX or whatever and getting all the processes on a system, but it's just kept in a nice pattern. Usually it's ordered by CPU down. So it's kind of like in Windows, you have the task manager, you can go in and you can see the performance. This is like that, just better. It also tells you stuff about the system, how many tasks are running, the CPU. You can see the percentage usage there, so that's sort of how busy the system is. You can see the total amount of memory. You can also, from options here, if you type H, you can see like threads, if a program is threaded or not. In this case, you can see this is an MPI code that's running. It's got 8 of them running, and you can see the memory, the virtual stack, the status, and then they're sitting at approximately 100% CPU for each of them, except for one here is showing it's in state D, and that's Okay, so a system time is the time, your code is the time spent in your code versus the time spent the operating system is doing something. So your code is literally in your code doing something, in your loops and whatever else. System time means whatever the operating system is doing and your code has had to stop and wait for. So say you do a print statement. Well, your code stops, goes out, calls something to the operating system, it dumps something out and comes back in. So your code has kind of been paused. So it's kind of like it is still part of your total time that your job took, but it's not really due to you, right? It's due to what the system has to do. So it's kind of like, that's why it breaks it up. So there's the three parts, right? So your time plus system time will add up to the total wall time. And you care about that because it affects you. You know, if you're spending 50% of the time waiting for things, you're either calling something too much, or there's some sort of, you know, issue with that. So that's the difference there. Yeah. Yeah. So this in this case, it'll show to when normal top, it's going to show you the total per process. So it's all by PID. Now, if this was threaded, and you say you're running OpenMP, you may actually see, and say 8 threads, this may actually be 800%. Now, there's an option in, because it's still one task, and then there's sub-threads behind that. And when Ramses gets into the OpenMP stuff, he'll describe that better. But basically, there's an option in, by default, it won't show you the threads. It only shows you PIDs, like individual tasks. But you can press H, and it actually will break down all the threads. Then you would see what's going on with each of your threads as well. So that's another useful tool when you get into looking at threading. Now, in a pure MPI code, with no hybrid, like no threads, you'll just see the individual tasks. So you should just see 100%. And so on a system like this that has 8 cores, you should, you should be able to see as many of these up to 100%. You know, you can be 8 of those, right? Depending on how many cores are in the system. These are so a serial task, the best it can do is 100%. Now, most of the time, these are going to be 99 point something, right? What do you mean add up to 100% in terms of the? Okay, because, well, on a system that has 8 cores, you can theoretically do 8 serial jobs at 100%. Right, so 800% is your total, right? Theoretical, right? That system can be spent on. So you could either have 8 individual tasks, which is what's showing here, that would sum up to 800%. So that would be 8 100%. But if you were running a threaded code, you could have one task that is using 800%. Because under the hood, it's parallelizing under the hood. It's all a matter of task versus threads. I don't want to get into that too much. We'll get into parallel stuff a little more specific. I'm just saying this will show you some of that breakdown. But for serial processing, yes, it's just 100%. And if you have multiple cores, if it was a 20-core box, then you could have 20 running, and that's allowed, perfectly fine with that. And you can actually have more than that with hyper-threading and some other stuff. But we're not going to. I don't want to get bogged in the weeds. There's a lot of reasons now that you can swap out stuff to get better than what you theoretically think you can. But for just a basic serial performance, you want that guy to be 100%. As best as possible. Otherwise, you're spending too much time in system time. So top is useful. If you type M, you can get, there's a menu with all the different options. You can do memory first if you care about memory. Virtual stack, there's a whole bunch of options there. It's a very useful little quick tool. Just type it on the terminal, and it gives you a very text sort of based way of seeing what's going on. And you can see active systems. So you launch a job, and you want to see, I wonder how it's doing or how much memory I'm using. You can just log in and type top and see your job. You don't have to attach it. It's non-instrumented. It's just a way of seeing something as it stands. You can also see if you're growing dynamic memory, you can see that this will change. This has a refresh rate, and you'll see it change as the jobs run. As I said, I don't want to get into too much details of each of these tools. Just I want to kind of put them out there. You guys go play with them because I think these are very useful just things to know as you go along. So those are the non-instrumented ones. Let's talk about how would we instrument something. So a very simple thing is let's take a little tick-tock type time calculation. So you can use this. There's a million versions of these where there's a clock built into the system, and you can basically instrument sections of your code. You're like, I want to put into my code. I know I want to put in some hard times so I can measure. I don't care about I/O, so I only want to start at when I start doing iterations and end. So you can create a little timer where basically that's what the tick-tock here does. Well, you start time, you end time, and then it'll just calculate how many microseconds that actually took. And this is using the get time of day system command. So of course it's going to be a little system specific. This isn't going to work on Windows, but this will work on any Linux system. But there's a million variants of this. And the idea being is you're going to actively instrument your code. So you're going to say, okay, start clock inside your code somewhere, end clock, and then it'll give you a time for that section. Now you don't want to do that on every line of code, but it can be useful in large chunks of different sections of your code, or if you really want to get into debugging, so you can actually trace it as you go along. And then that way, as you're running things or making changes, you can quickly see, as I make that particular section of code, I can see if things are going faster or slow. So once again, I got to replace these codes because that's not very reachable. The slides are on the website. Sorry, I got to pull those out. I didn't think it'd be that bad, but basically, all that's really going on here is a simple matrix vector multiply. There's just a loop that's going to multiply two matrices, and all we're doing is we're putting in timers around those sections just to find out, what's going on and where is it spending the time. It's doing nothing more than, setting up a matrix, reading it in from a file, and then multiplying it. So initialize the data, does the multiply, saves the result. So really, there's only two sort of things that are going on in here. There's a loop that does calculation, and there's a loop that does sort of the I/O type overhead, right? And there's some options for like the size of it. So since you can't read the code, we'll just skip that anyway. You run it, all it really does is you give it the size of a matrix, and then because it has those two timing loops set up inside of it, initialization, that's just creating the initial memory. The calculation, where it actually does the, xij times bij, and then you actually get the total time. And as you can see in this one, I'm spending almost all of the time reading in the code, reading in the data, or writing it out. It's because I/O is a huge bottleneck in this case. I think I've got it better. Yeah, here you can actually see it better. So at least this part you can read. And this is primarily because the I/O is being done in ASCII. So we're not writing in binary. We're just writing the ASCII files where we read this in. We're just f-printing in from C, this vector here. And because this is such a large matrix, when I try to write it, we're literally writing, over 6 million write operations. So that's horribly inefficient. It's still actually not too bad. You can do that in 5 seconds. But the thing is, relative to the cost, it's a bad idea. So obviously, that's an easy target or low-hanging fruit. Let's just replace that one function with a equivalent binary writer. So instead of us going fprint f for each one of those little entries in those matrices, we're just going to take the full vector. We're going to fwrite the whole size of it as 1. So we can fwrite the whole thing. So this is just the binary equivalent of an fprint f, but we're actually going to take the whole matrix and just dump it. So there's no conversion in that system time. It doesn't have to take, a binary number, convert it to a string, and then dump it out one at a time in a loop 6 million times. It just takes it right out of memory, dumps it to a file. So it can stream the data just in one big chunk. So now we can try it again, and we can still see it's still one of the bigger significance, because this is it's one of our toy problems, but it's way, way, way more efficient, about 36 times faster. So there's sort of two things to know there. This is one of the things we always harp on is don't use ASCII files unless they're great for testing out stuff, but you can see where you can easily become complacent and it starts adding up and spending a lot of time doing stuff you don't want. It's better to have at least both options so that you can, when you start running real calculations, you don't spend with that overhead. But you can also say there's a simple little instrumented version of your own code where you're not instrumenting every line, but in those main features you can put in just a tick and a talk timer to kind of give you a feel of where, maybe I forgot the ASCII option on by mistake, right? As you can see, also the I/O file, if we look at it, this is 89 megs, this one's only 20 megs because there's no empty space in it. So it's always better from that too. So it's just an example of doing a simple thing to know, you could do this to the 5 parts of the main piece of your code or something. But it does require you to instrument it, and it's not quite as portable, right? Because now you've got some system calls in there. It's not a big deal. I mean, this is a couple of lines of C code in there, and you can do this in Fortran, you can do this in C++. It's all the same stuff. Does that make sense? Okay, so always use binary. We have to stick that in all the time because You would think that's something simple, but it always becomes an issue with a lot of these codes. So sampling is, so that was a direct instrumented approach. And it works great, but it's really going to be a pain if I've got some new code that Ramses wrote when he's very verbose and it's got 40,000 lines of code because it's C++ and it's got a million structures. And I don't want to have to go in and wrap all my functions with time codes and try to figure out where they are. Shouldn't there be a way to do this for me? Well, the good thing is yes. And most of these will sample this as you run your code. And the idea being this is you don't have to track every individual function call. Because if I'm calling 6 million times a second or something, I probably only need to make that timer go off every couple of hundred or so that I don't get the overhead of it. I can just sample it and get a statistical representation. Because I don't really care, most of the time, I don't really care if it's 93.77725 version of my code. I just want to know, to sort of engineering precision, what's going on. So if I sample the code relatively fast enough, or with detailed, I can actually get a pretty good representation without actually having to track every line. And we don't want to instrument, and we should have, let's let the compiler do some work for us to do this. So this is still very out there. But basically the idea being is the program executes as it's running, and then every so often, say every 100 milliseconds, the timer goes off and then takes statistics about how often that function was called. Then it knows, okay, this was called, it takes 0.001 second, and then at the end it adds them all up and gives you, as a percentage of your total, now I know how much I've spent as a function in that time pipe. And it tells you slow where it is. So let's try it for this code. So it's very low overhead, no experimentation. You didn't have to, in this case, we're just going to add a compile flag. We don't actually have to put anything in our code, change anything, it's literally a recompile. And the disadvantages are you don't know exactly every line. So if there is 10,256 calls, you may not know that exactly. You'll be within a fairly good number. And actually, with most of these codes, the sampling is pretty representational. But it's not perfect because it's statistical. And you have to run long enough. You can't just run a 0.01 second code. You got to run a few minutes to be able to get, or maybe not even a minute, but long enough that you get enough sampling statistics out of that. So how you do this is just like adding the debug flags. You add -G to any compiler, and then you add -PG. So it's called PG or profile to guide it. Basically, it just adds it in, and all this does is tells the compiler, says, okay, turn the debugging symbols on, which you want so you actually can make it human readable. You don't have to, but then it told you what line of code is, you wouldn't be able to figure it out. So you want that so it tells you, line 52, function X. And then PG just tells it, okay, put in those extra timers around things so that I don't have to do it, but the code will have it for me to keep track of it. So then all you do after that is you run your code just like you normally would. And when you're done, it should run, you can check this with time too if you want to see how much effect that's going to be with and without PG, see how much effect that sampling costs you. It should be pretty marginal if it even shows up. As I said, the compiler's done a pretty good job of putting this in. And then you'll get this file at the end called, be all your normal data, but you'll get this extra file called gmon.out. This is basically all the sample statistics dumped into a file. Now that file itself is not directly readable. You need to run it through a tool called gprof. You can use other tools, but the easiest one is gprof. This is like GDB. It's like a new tool. So you go gprof by binary and the gmon.out, and it'll give you a flat profile. Basically shows you per function where all the time was spent, and once again, because it's sampling, you'll get a little bit of round off error. Look, I'm 20.24% better than theoretical. Now in this case, it's kind of trivial because you're like, well, that's kind of useless. Of course, I only have a main function. It doesn't tell me exactly what I want to know. Now, a lot of time in your code, you're going to have multiple functions, so this is still useful because you know, oh, I'm in this function, great. But it doesn't tell you exactly the line of code. Good thing is, because we had the debugging symbols on, we can add the -line option and then break it down to line. So now we can say, okay. Now we're inside main, and we can look, okay, I'm spending 68% of my time in the matrix vector multiply, line 82. And then I'm spending the second most chunk of time on line 113. So then I can go back to my code, simple enough, and say, I guess you can see that. On line 82, not surprisingly, this lines up with what we did in our instrumentation case. The line where I multiply my A matrix times my X vector, not surprisingly, that's where I'm spending all my time. And then the other time I'm spending on is when we're outputting this our data at the bottom here, line 113. right? That's the IO the old way. So that told us that exactly by just tracking the line down. So that's pretty straightforward. It gives you right to the point. Now, you still might have to think about it a bit, but at least it's pointing you in the right direction. Almost all these tools, that's what they're doing, is just you're spending some time here, go look at the code and figure out why, or maybe you just need to. In this case, there's not much you can do. That's where you're spending all the time. So gprof is really easy. It exists pretty much on any platform. You can do this with all the different compilers you're going to come across. It's easy to script. You can put it in a batch job. It doesn't cost you. There's no interactive stuff. You just run the code, turn it on. No big deal. It's low overhead. And then there's also, you can take that output, that gmon.out, and there are other tools, fancier graphical tools that'll organize it for you too as well. Overhead is just, remember we were talking about that system time? Overhead is anything that's not doing work, not doing practical work. Overhead is just the extra work. So if you ran this code without profiling and it took 1 minute, and if you wrote it with profiling that it took 1 minute and 1 second, that 1 second is overhead. And what you really care is the ratio of overhead to total program time. So if it's 1 second out of 60, that's not that bad, 2%. But if it was an extra 20 seconds, now you're having like a 30% overhead, right? Overhead is management, right? Those are the guys who aren't doing any work. You're paying them to do something to organize everybody else, but they're not doing anything. That's where the terminology comes from. It's a financial term. But it works the same way here. It's just the guys that don't do anything, right? It's true. Anyway, so yeah, there's tools that can go on top of this as well. Okay, so another part of profiling, we talked mainly about performance and timing, and that's usually that's where we most of the time care about. We want to think about, is this going to take me 5 minutes or 10 hours, right? But another aspect of that, and can be even a bigger deal depending on the problem you're working, is how much other resources are you using. So it could be disk usage. That could be a profiling thing. That's usually straightforward because it's linear. You can kind of figure that out by the file size you generate, right? But the other thing is how much memory. And this can be a trickier one to figure out because a lot of people, especially nowadays, in the early days, everybody cared about memory because it was a crazy scarce resource. You would, little tiny variables, you'd be doing all your work to just trying to fit into memory. Now, we've kind of gotten lazy because there's a lot of memory on most modern systems. Gigabytes, terabytes of memory on big systems. So most of the problems, especially when we're developing code with our toy problems, we never even have to think about memory. I'll just store everything, right? But when we start to scale out the problem or scale up the problem, we can easily blow out through that memory pretty quickly, especially if we were rather inefficient. As I said, we go from 1D, 2D, 3D, and now I'm storing everything and every vector and everything else. And we tend to trade it off saying, oh, I'll just store it so I don't have to recompute it. And that's not always the best thing to do. So we need ways to look at memory usage as well. So the first easy we do is in that top, we can see that right away when a code's running. In top, we could actually see our current memory usage. So that's a very first order way of doing it. Let's talk about other tools to do a little more investigative one. So Valgrind is a tool that actually has a whole bunch of sub-tools, but it's a group of tools that do memory interactions. It was originally designed for the KDE graphical desktop, but then it's become a much more powerful tool across multiple platforms to be able to look at how memory interacts with the operating system. So one thing you could do is you can run a heap profiler. So Valgrind, and this is good, you don't have to instrument your code for this either. Usually just compile with the debug, you don't have to change your code, not anything else. You just run it Valgrind, tool Massif, and then my code, and it'll give you kind of like the gmon.out, massive.out, and you go msprint, and it'll give you a dump of where all the memory accesses were running in your heap memory. So it can kind of give you a map of where your memory has taken place. So this can be very useful if you're doing dynamic memory allocation and you want to figure out, which parts, where's all my memory going? I'm doing a rough calculation. I think I should be using 2 gigs, and suddenly my code is using 10 gigs. Why? And this is a way to doing that. It also has a cache profiler into it. So the cache is the very sparse memory that's on a CPU, that's directly on the CPU. Super, super fast, but there's not much of it. And ideally, you want to be able to move data in and out of that really efficiently. And this is a way of checking that. Randy in the next class is going to get into caches and how that works in general, but this is a tool that allows you to investigate that. And actually can have a huge deal on performance because if you're what they do call cache thrashing, you could severely slow down your code by 2 or 3 or 10 times if you do that wrong. So this is a way of investigating if you think you're related to the cache. So here's an output from, this is like the gprof.out of a CFD code that I had here anyway, where I basically dumped the code, and it's sampling it, so n times, so you can see here. Once again, Valgrind is a very useful tool, but it will take a while you staring at the output to figure out what's going on. It is very, very verbose. It does things like you can check memory heaps, you can check all your memory leaking if you're worried about that. It does all that stuff, but it's very verbose. So this isn't too bad. It just shows you the current stack of what time it was, what the total memory was, the total heap memory. So you can see it's pretty constant for this one. And then it tells you where the percentages in each of those memory was being held. So it brings it right down. This is a C++ code to individual lines, or effectively classes, where each of these pieces were. Right? So think of it very analogous to what we were getting out of gprof. Line of the code. Now with memory, it doesn't mean it actually was allocated at that point too. It just means when it was sampled. So that can be a little bit, it's not like a timer. It's more of a, you got to kind of think of it in that context, right? But once again, Valgrind, when you think memory, think Valgrind, and there'll be some tool there related around it that will help you. And you can run Valgrind in parallel too, with MPI codes if you need to. Okay? Oh yeah, the one thing that we talked about overhead, Valgrind is slow. Because what Valgrind does, instead of instrumenting your code, it sits between the operating system call and your code and catches every one of those calls. And some are more, like when you're doing the memory checking, it actually checks every one. So it can be literally 10 times or 20 times slower running your code, which is fine. Just don't try to run on an hour-line code. You know, if it happens in the first 1 minute, no big deal. It takes 20 minutes. You can test it. But it actually does add a lot of overhead, because it literally says, okay, you're going to make a memory call. I'm going to look at you. I'm going to bookkeep it and then send it on. So it's like, it's like checking every car that comes down the highway. It's going to slow the whole process down. It's great because it can track that detail. The heap profiler is not that bad, but the memory, when you do the mem check stuff, it is very slow. It's heap versus stack memory. So it depends on, there's different types of memory, right? So heap memory is just the allocatable memory. That's where most of your memory is going to be spending, right? We can get into, I don't want to get into the whole details of that. Basically, there's different types of allocation memory. When you dynamically allocate memory, the memory is going to be sitting on the heap. Right? So that's where your system memory that you're accessing into it. There's a hierarchy in memory, and most of the time we gloss it over. Nowadays, especially too, we're talking about cache, stack. It's just how the program allocates different types of variables to different types of memory. So this one in particular is looking at the heap memory, which is the one that any C and C++ are going to. Most people that worry about stack memory, or if you're old Fortran programmers, you blow through your stack all the time because they allocate everything on that stack variable. But we could talk about memory for days here, so I don't want to get into that too much. Okay, so other profiling tools that are out there. There's lots of them. Scholastica, Tau Performance, HPC Toolkit. These are commercial ones. Allinea, Intel's. If you got OS X, Xcode, their developer has tools in it as well. These two as well, the Intel V2, and if you have any of the Intel compilers, these work well. This is the debugger, but it also has MAP, which we'll talk about in a minute here. That also gives you performance information. If you're doing a GPU, the NVIDIA gprof, like a gprof, but for an NVIDIA GPU, has that as well too. They're all doing the same thing, just various checking. Some of these toolkits at the top are really designed for parallel codes, for determining how well your threads are doing or how your tasks. The two that we haven't signed out, the commercial ones I'm just going to mention here, are Intel Parallel Studio. This comes with, if you get their full kit, it changes names every year, but basically it comes with a whole bunch of very powerful tools. VTune, or what they call Amplifier now, is a good performance one. This actually looks at your kernel and actually checks what's going on. It's a little hard to run in the cluster, but if you have any of those tools on your desktop, it's a nice little GUI. You launch it up, you launch a test, and it gives you all the statistics, kind of just like running gprof. Right down, and it'll even give you advice about, maybe you should spend some more time at heat maps, red here for where you're spending all your time. So these are useful tools. There's an inspector, which is kind of their version of Valgrind, not quite as good, but it actually has a memory mapper in it as well. Advisor really is more of a thread or a vectorization tool. It's there for, it looks at your code and says, you've got a loop for AX times B. Maybe you should be able to thread it or use their vectorization tools. So the vectorization is using special instructions in the CPU to do multiple things at once. So instead of just going A plus B, it'll take A1 to 4 and do all of them at the same time. So that you've heard, there's lots of terminology, AVX and SSE and all this stuff. This will help you tune that either intrinsically or use certain libraries to try to help that. So that's a little more performance-based as opposed to inspector, but the vTune is kind of the overall tool. And they also have an MPI trace analyzer, which is useful for figuring out what's going on in an MPI code. And you can use those on SciNet. To various, the full vTune doesn't quite work because there's some kernel modules and stuff they have to, but they're there, and just if that's something, if you have the Intel compiler suite on any of your workstations, it can be quite useful to dig into your code. One that we do have that works quite well on SciNet, that is the DDT library, which is their debugger, but it's also they call now Allinea Forge, which is their profile debugger and all these tools. They'll probably change the name again because they were bought by ARM, but I guess it's Allinea ARM now. Anyway, but same company. It's just basically it's the same tool, and it has they have sort of two pieces that you can get performance information. One's really simple. It's called Performance Report, and it really requires you to do nothing. You just go Performance Report and then run your code, an MPI code typically, that you normally run, and it gives you an HTML file with little plots. I think I can look at it the next page here. It says, oh, here's a quick report card of how what your code did. It tells you what it was running. It says, oh, your 86% of your time was in compute, 13% in computation, doesn't do any I/O, so that's not a problem. And then it gives you some further breakdown of what's going on. So in the CPU time, you're spending 53% doing scalar operations, 3 in numeric, but I'm hammering memory pretty hard. So you're like, oh, maybe that's something I should think about. MPI, you're spending, oh, look, 100% in collective times. Oh, that's where I'm spending all my time. And this didn't cost you anything. It just ran while your code ran. And it kind of gave you a quick summary. Okay? As I said, it's a commercial code, so it just dumps out this HTML file and you can look at it. And that's available on our system. So that's performance reports. The other one, which is a little more detailed, which is kind of the profiling part, is the MAP. I think they still call it MAP. But anyway, inside when you load up the program, it's called MAP. And you compile with the debugging flags on, then you run MAP. And you can run this on SciNet as well. It's commercial code, so it is licensed depending on how many cores you want to use. You can run that, and this will actually give you a whole bunch of output data like the gprof that you can then pull down the menus and see all the sampling traces as your code runs, and you can watch your memory. Here I've got it just pulled up for MPI calls, so this is the parallel library stuff because I was moving for that. But you can see the memory usage over time. You can see all these nice sort of time histograms that gives you all the details. And it actually points to the line of code. You can click on it. It's very, very well put out, GUI sort of type of setup. It makes it very easy to drill down and look into sort of core times. You know, you can see the histogram over time. You can highlight a section and blow it up and say, oh, this is what's going on. You can kind of see trends. And so anything in green is CPU. Anything blue is memory. And you can see that over time on this one. Or I think, oh no, blue in this case is MPI, sorry. I think you can also there's a lot of memory options for MAP as well. We do a whole course on Allinea's type products, but it's pretty easy to get going. That's the good thing. It's all, you just pick your program you want, and then you can just play with the menus and look at all statistics and stuff. But it gives you a lot of data from sampling as it runs your code. So it's a good way of sort of figuring out if you're not quite sure where overhead is, either is it a parallel part or is it a memory or this type of thing. It can give you a lot of good details about that. So I just want to do a quick summary here on profiling. You know, you can instrument your code, and it's always good to do some level of this. You probably already do that. The very fact that you output, you know, each iteration one or finished reading an you're already instrumenting the code to tell you something, right, as it goes along. So you can put in some bulk timers to do that as well, just to kind of keep track of, oh, spent 35 seconds doing this on 32 processors. Perfectly reasonable thing to do. But you really don't want to do that for everything all the time, because then that's extra overhead you're just adding, and it's just too much information, right? So a way of figuring that out when you sort of know your code is working properly, but you want to really understand it, you can just use one of these you know, profiling tools to figure out what's going on at a particular time. The other thing that both Allinea and the Intel do is you can run it, make changes, and then run it again, and they'll compare the two reports. So that it can kind of give you that sort of experimental approach where you can look at changes over time within a project and it'll actually compare those. So you can say, oh, look, now I've sped up this one, and maybe it's moved my bottleneck somewhere else. So I just meant that's a useful thing too. So the whole point of this is just to try to get you to quantify and know where the expensive parts of your code are. For two reasons. One, just know that that's the expensive part. Maybe it just is. That's where I should spend my time or change my algorithm. Or just know if that is the expensive part, how to minimize it, or just at least be aware that maybe that's, is there anything I can do? So at least know where I should spend up. And this is important too, especially if you start looking at serial codes and you're like, well, now I know the expensive part in a serial code, maybe that's where I should focus my parallelization on. There's no point parallelizing something that's only taking 0.01% of my time. So that this will come up when we talk about threading and MPI. Now that I've gone through this analysis, maybe I should, that's that vectorization. I can easily vectorize that or that multiplication of my matrix multiply and thread that out or do other mechanisms, right? And the other thing just to keep in the back of your mind, Valgrind is the tool that you should think of when you think of memory problems. That's one of the first things we'll ask you. It's pretty easy to do. Yeah, the output's a bit long and tells you a lot of details you've never heard of and uses terms like very operating system level heap and stack type commands all over the place. But in doing that, you'll learn quite a bit about what's going on that you may not even have thought about before, because it's intercepting all of those details of your code. The last little one I think I just have after the end here is just I put a little bit of detail in here. I don't want to get into too much, but this is we mentioned it in the Valgrind context, this idea of cache. So cache, just to reiterate it, it's the part of the memory, it's very small, that's the top level of the memory hierarchy. So that's ready, but that's on the CPU ready to do some data. Or do some calculations. So that's where the CPU is getting data directly. The cache is going to copy memory out of a lower level cache, which is going to copy memory out of your system memory, right? Your regular allocatable pool of memory. But this cache can be quite small. It's usually only a couple megs. So if you're doing your matrix vector multiplication, it's not going to load the whole matrix in. It's only going to load in the local piece it needs to do that data, depending on how much data it can get. So memory bandwidth is really, really important for good performance. And this, of course, is the fastest memory. It runs, so just for a normal CPU, say it runs at 3 gigahertz. The cache memory will run maybe half that speed. But your system memory is only going to run, 1/5 of that speed. So that means every time the CPU is waiting for a piece of data, it's waiting 5 times longer. Okay? So making sure that you're not waiting, especially on something like a GPU where it's even huger chunk, is key to making sure your performance is good. So you want to make sure that it's not waiting on data to copy into the cache while I can do a calculation. You want the data on the array information I need on that cache to be available. Okay? So main memory is big and slow, cache is small and fast, and it saves the recent access of data. So if you went and said, I'm going to calculate the next 100 variables of this vector, it goes and gets the whole 100 at the same time, right? Well, ideally, you do all your calculation with those 100 and not just have to skip and throw out the next one, right? So this is all about keeping that cache in a way that makes sense. So when you access the memory in order, i.e. it's a 1D vector, you go 1, 2, 3, 4, 5, nice and ordered, so it goes and gets that one cache call, and then it can actually it already has that information for 1, 2, 3, 4, 5, right? So you're not wasting extra call there. So that's ideally what you want to do. But maybe you're doing something in a funny pattern where you're actually going 1, 57, 98, right? And if you do that, the CPU, the memory profile or the memory prefetcher is going to pull just this line, but then you're going to stride it this way. So what you're forcing the CPU to do, and it'll do it, it won't complain, it'll do it anyway, but it's going to have to get that whole line and then throw it away and then get the next line and throw it away. So you're spending a lot of time doing stuff that you might not want to do. So they call this a cache miss, because basically it went to get the information from the cache, didn't have it. So it had to send it out to go get it, which means it's going to slow it down. And you can see very, very slow times. Now, modern CPUs, especially Intel CPUs, are very, very good about avoiding this type of thing. Almost too good a little bit. They actually play games with prefetchers and stuff to look way ahead of what's going on It's like going back up the line and asking everybody what they want ahead of time so that it has it ready and reorders things. But you don't want to rely on that. Ideally, this would be nice and ordered. And you're like, I don't really care about this microarchitecture stuff. You're using terminology I don't want to know anything else. Well, I'll show you how this affects real code. So where this comes down to it is literally how you want to stride your memory accesses. So in a matrix vector, you know, I've got ij. We always stress about which order matters. Well, that's because we know that memory in 2D is really memory in 1D, right? There's no such thing as 2 or 3-dimensional memory. It's all 1D. It's just this plus an offset. So in C and C++, we always want to decrement the last index first, the highest index, because that's why we put the I on the outer loop and the J on the inside loop, because that's going to order the memory like our first case. Right? So we go I, J, J, you know, then J1, I, J, whatever. We do it the other way, where we flip those. Oops. Then we would get J, J, oh, see what I mean? So that matters, yeah. No. Well, because it can't change the order, those type of operations. You're not telling it. You're telling it explicitly to do it in the other way, right? So some of these tools will tell you that you're doing it in the wrong way. So that's what the cache tools, the cache missing will tell you. But the compiler itself can't go and rearrange your data because maybe I need to do it this way because I do this one first, then this one, and then change this piece of data, right? So where if I went it this way, maybe it doesn't matter, but the compiler doesn't know that it doesn't matter. And if it doesn't matter, you shouldn't be doing it that way, right? So this is why it's convention, right? So that's why it's good to, you know, most of us you'll always see us write one way, and that's because we're trying to ingrain and it's not for this type of thing. There are other more complicated cache patterns and stuff, but you can test this out yourself. This is a very simple case to figure it out, but how much can it read in the cache line? That's a more trickier problem because it depends on the architecture, the processor, and a whole bunch of other things. Because if I go on your laptop, you may only have, whatever, 512K of memory per core. But on a big server class, you may have more. And on a power, you'll have a huge chunk of memory. It's more of the convention is the prefetcher will do its best to take multiple of those lines. And if this is really small, like this is 10 by 10 or something, it won't matter because it's going to suck the whole thing in, right? The point is if you do this in the right order, then when it does become an issue, you're trying to do it in the right way to begin with. But yeah, if you really get into individual processor tuning, that's a whole other ball of wax. And that's where the cache tools, cache profiling, would become more of an issue. That's where you actually have to use the tools. I can't tell you a priori about that because it's going to very much depend on the CPU you're going to use. But I can tell you that it's always better to do it this way. So these are the type of things from a code level without actually having to get into specific stuff. Just they're good habits to get into. So I didn't want to get into too much with cache and that sort of thing, but cache grind can kind of give you a tools, and this is a graphical front on the top of it where it can just show you, where you're spending your caching, hitting, and all this sort of details. As I said, Ramses is going to get in this a little more detail next week. I just wanted to point it out because it kind of goes with the Valgrind as the tools, right? So most of the time you don't really have to worry about it. Luckily, we've gotten with regular homogeneous programming. If you're talking GPUs, it matters more. But for regular stuff, we don't have to worry about that much. Just there's certain conventions, stick with them. And pick. There's a reason they're done in one way in Fortran and one way in C, because that's going to be the more efficient way. And if you want to look into it more, there are tools that are going to help you figure that out. Okay? Is there any questions about profiling or performance? We'll talk about this more as we go along in the parallel sections, because these become more important, especially when you're doing parallel work, because it's hard to know where things are happening. But just be aware there are good tools out there. You don't have to instrument it all yourself. And it's a good habit to get into. Just like using a debugger, running this periodically will tell you, am I making any progress? Or am I just spending all my time making the code look good but not be any faster. Okay? I think that's it then.